In the third part of the lecture, we will give overview of other segmentation methods. This will include thresholding and region growing, graph cuts, active contours, and level sets. This part is new, so you are not required to watch an external video anymore. So let's start with thresholding. This is the simplest and sometimes very effective segmentation technique. And the key is to find the threshold automatically. And one good method to do that, it's Otsu method. And in Otsu method, we find threshold that minimizes the within class variance. And you already know this criterion because it's the same as k-means. So just to remind ourselves what is within class variance, that's this sigma squared here. It's a weighted sum of individual class variances, so variance of the intensities within each class, and it is weighted by the proportion of the samples in each class. So here is the explanation of all different variables. But what is different about Otsu method is that is optimization. So we use brute force search, and that means we search through all possible thresholds on a grid. And this has an advantage that it's robust. We always find a global solution, so it doesn't depend on initialization like k-means does. But the disadvantage is that it's more computationally expensive. And this is especially if we have higher dimensional problems or multiple classes. This is an example of an Otsu method. So here we have cardiac MRI. And we would like to threshold it. So here you can see the image histogram, and it turns out that optimal threshold that results in the smallest within class variance is around 0.39, and this is the result you get. So here you can see nicely the ventricle. Alternative to thresholding is region growing. So it is different because in thresholding, we just threshold the image intensities. But with the region growing, we start with a seed point and grow from the seed point until we come to some image edges. So we basically want to include all the pixels that have similar intensities. So we start from one or more seed points. So it's YS here, that's the intensity of the seed points. We will look at all the neighbors that are similar, and we will continue looking at the neighbors as we grow this region and adding them. So unlike in thresholding, the resulting segmentation will be a single connected component, as we can see here. So just the ventricle and not the other stuff in the image. So example of the similarity that we can use, it's intensity difference threshold. So we will only add pixels that have a similarity to the current pixel, a difference to the current pixel smaller than a threshold. Yeah. So let's have a look at the algorithm. So we start by, so we will have a queue of the pixels and or voxels if you are in 3D. And this queue are all the voxels that are waiting to be processed. And the first one in the queue will be the seed point. And every voxel or pixel that goes into the queue is marked as visited, and the visited pixels and voxels will be the one that will end up in our final segmentation. So we start with the seed points in the queue, and then we will continue in a while loop, and this while loop will run while we have something in the queue, so while the queue is not empty. So let's have a look what happens within the while loop. So first, we get a point from the queue. And when I say we get a point, I mean that we will take it out of the queue, so it will not remain in the queue, okay? And then we look at all the neighbors of this point. And for each neighbor, if it is not visited yet, And if it fulfills the similarity condition, so it has similar intensity, for example, then we will add it to the queue and mark it as visited. So it will be part of our segmentation, and we will keep growing around this point as well. So that's the whole algorithm is actually very simple. And as I said, the final segmentation will consist of all visited points. So here you can see an example here. We have a CT image, and the aim is to segment the lungs. And in this case, lungs consist of 3 connected components. So we need to put these 3 seed points and a region growing nicely created these 3 components of the lungs. This type of methods is particularly suitable for CT because in CT the intensities are reliable, so the tissue properties result in particular intensities. This is not the case in MRI or ultrasound, so region growing might not work so well. Another very popular technique, it was one of the most popular segmentation techniques just before the deep learning appeared, is graph cuts. So this is based on graph theory, and the image is used as an undirected graph here. So for each pixel in the image, we have 2 variables. One is the observed variable, that's the intensity of the pixel, and another one is the hidden variable, and that's the label that we don't know and would like to know. Okay, so these are our graph nodes, and now we want to work out what are the edges. So basically these variables are organized in a Markov random fields, and these Markov random fields defines which variables are dependent and which are independent. So first we'll say that the label, each label is dependent only on the neighboring labels. Yeah, so if we take this label ZI here, it will have an edge to all its neighbors. So the edge means that they are dependent. So, but it will not have an edge to any other. So only the 4 neighbors if we are in 2D. Then each intensity is dependent only on the corresponding label. Okay, so here we have XI, intensity XI, and it's connected to the label ZI. So there is an edge here, but intensities are otherwise independent of each other. So we have no edge between the neighboring pixels for the intensity variable. Okay, so this is our graph of dependencies, so our Markov random fields. So these edges show that 2 variables are dependent, and we call it 2-click. All right, so defining these dependencies and independencies helps us to model the probabilities. Without that, it would be intractable. No, now, okay, fine. We have the graph. So how do we find these hidden labels? Because this is what we are interested in. So we know all the intensities, all the blue ones are known, but we want to know the red ones. That's the segmentation. That's what we want to find. So to do that, to find the labels, we will maximize the posterior probability of the labels given the intensities. So here the Z is vector of all the labels and X is the vector of all the intensities. And we want such probabilities Z that they are most likely given the intensities that we have in the image. Now, some equation here. How do we go about it? Because we don't know what to do with probability. We need to somehow transform it to some kind of function or a criterion that we can optimize. So we already said before that it's much easier to optimize logarithm of probability because multiplication changes to sum. So, and first thing that we will do with this posterior probability, we will apply Bayesian formula. So because we working with logarithm, we will get a sum of 2 probabilities. So this is log likelihood and this is log prior. There should be a third term as well, but this term is not dependent on labels, so we can ignore it because it will not change anything on the optimization. Okay, so this is likelihood of observed intensities given all the labels, and this is prior for all the labels. So now we need to unpack these two terms, because now that's a joint probability that is like a very big thing that we can't optimize. So we will use this graph here, which gives us the Markov properties for these variables, to create the likelihoods and priors for the individual variables. So we said that the intensities are not dependent on each other. That means that we can multiply individual intensities, and this is conditional on the labels. Okay, so basically this log probability will become a sum of log probabilities for individual intensities given the labels. So we sum through all the pixels. So we will have one for each pixel. And we don't really need to keep the whole vector, because this graph tells us that this intensity is dependent only on the label of the same pixel, but not the other labels. So that's why we can drop all the other labels. So this gives us the likelihood for each pixel. Okay. Then the prior is the second term. And here we again need to use the Markov properties. So now we are on the red labels, and we need to look at all the edges. So we cannot just multiply the probabilities on individual labels, because they are dependencies. But thanks to the Markov properties, we can make it as a sum of the probabilities of 2 clicks. And for each of these edges, red edges, we will have one term. So we will have a probability of current label ZI given label of its neighbor. Okay, and we will sum them up through all the neighbors and then through all the pixels in the image. So all the 2 clicks that we have. All right, so we have our objective that we want to maximize this posterior probability. It's called sometimes maximum a posteriori. So when we want to look at it in context of graph cuts, we tend to talk about energy rather than the posterior probability. And the energy will be minus logarithm of posterior. So we can call it a negative logarithm of posterior of the labels given the intensities, and this will be our overall energy EZ. So you see that it's dependent on all the labels, and we want to minimize this energy, right? We were maximizing. If we put a minus, we minimize. Now this energy will consist of 2 terms. It just follows this equation here, like this, consists of 2 terms, so likelihood and prior. So that will be rewritten as an energy. So minus, so we will have unary potential energy that is potential of each individual label. And this will be the minus log likelihood, negative log likelihood. So it will be probability of intensity given that particular label. So that's the unary potential, and we will sum up through all the pixels. And then we have a second term that will be pairwise potential. So this is minus logarithm of probability of current label given its neighbor. And that's energy for the pair of the neighbors. So that's why it's a pairwise potential, and we sum them up over all the clicks. And basically this unary potential create the data terms. So these data terms wants to make sure that the labels correspond to the image intensities that we've got. So that's our data. And the pairwise potential create a smoothness term. So it ensures the smoothness of the segmentation. Now, how do we define these potentials, these energies? So a very common way of defining unary potential will be simply square distance from class mean. So if we have 2 classes, then we can just calculate the square distance from class mean, and that will give us the unary potential. So if you notice this energy, we will minimize it. So we will basically want to choose the class that has a mean that is closer to the intensity. So it makes sense. We want to minimize this difference, yeah, to minimize the energy. Now, the pairwise potentials will penalize different labels for next neighboring pixels with similar intensities. Okay, so if the pixels have neighboring pixels have the same labels, there is no penalty. But if they have different labels, then we will want to give a penalty. And this penalty is modeled as a Gaussian of the intensity difference. So if the intensities are exactly the same, then we will get the highest penalty because it's same intensities, different labels. We don't like that, so penalty is high. If the intensity difference is very large, then the penalty will be small. So basically, if we want to minimize this energy, then we want to put an edge in the segmentation where there is big intensity difference. Basically, that's what this term will result in. Now, so we have the objective here properly defined. We have an energy that we want to minimize. So now the question is, how do we go about this? And it's not very trivial because we have all these pairwise potentials there. And one of the cool algorithms that actually solves this problem comes from graph theory. That's why we talk about graph cuts. So we will minimize this energy using minimum cut, maximum flow algorithm. So the energy will be actually equivalent to the minimum cut. So minimizing the energy will be minimizing the cut. And actually that corresponds to minimum cut corresponds to maximum flow within a graph, within a weighted graph. So now we need to convert this image into a weighted graph to calculate the minimal cut using this algorithm, and then we will get the segmentation. So once we have the cut, we sever the edges, and we will end up with two separate graphs that are not connected to each other. So two components that are not connected to each other, and that will give us the separation into the two classes, so segmentation to foreground and background. All right, so let's discuss how we will create this weighted graph. So nodes will be image pixels or voxels. So each of these pixels will be a node. You can see them here. And we will have two special nodes that are called sink and source, and then represent foreground and background. And basically, idea is here is that this flow goes from sink to source. Yeah, from source to sink. Sorry, so everything flows out of the source and flows into the sink. And then we want to find maximum flow through this. So we need to see what are our edges and what are their weights. So we will have edges from both sink and source to all the pixels. These are these ones. And they will have weights that are equal to unary potentials. And then we will have also edges between pixels on the grid. So just to the neighboring pixels, and the weights will be the pairwise potentials. So in this understanding of the graph as a flow, the edges, the weight of the edges represent the capacity of this edge. So how much water could flow through this edge. And we want to find the maximum flow through this algorithm. We want to, through this graph, we want to calculate how much water can flow through it. And to this, there is a theorem that states that this flow can be calculated as a minimum cut through the algorithm. Okay, so we will not go through this algorithm because that is quite complex, but it's a very well-known algorithm from graph theory. It's called Ford-Fulkerson algorithm. If you're interested, look it up online. You will find a video, I'm sure. And this algorithm will help us to find this minimum cut, which is the same as minimum energy. So the cut means set of edges that if we remove them, we will separate a graph into two connected components, and one connected components will be connected to the source and the other one to the sink. And the capacity of this cut will be just sum of the edges that weights of the edges that we removed, and that's exactly our energy term. Okay, so if we find the minimum cut, we will minimize this energy, and then that will result in the segmentation. So a major advantage of this algorithm is that it offers a global solution to the minimization problem of this energy term, which is not the case for like EM algorithm or k-means that we've seen before. So that's a great advantage. But the disadvantage is that this comes at a computational cost. So usually if we just have binary segmentation, this tends to be okay. But if we increasing to multiple classes, it's a hard problem. Now, so far, we have always considered voxel intensities as a basis for a segmentation, but there is a completely different set of methods that fit a curve or surface to the image edges. So first of all, let's have a look what is a curve. So curve is a mapping from one-dimensional space to two-dimensional space. So in one-dimensional space, we have parameter P, and this parameter, you can imagine it goes around the curve like that. And then the curve is the output of this mapping. So for each parameter P, we will have two output values, which is the x coordinate and y coordinate of the point of the curve. So if we take P here, then we get x and y coordinates of this point. Okay, this is how we define the curve. And here you can see such a curve starting from just a square and evolving until it sticks to the edges in the image. So let's have a look how this is done. So the question is, how can we evolve the curve to fit to the edges in the image? So first of all, we will move the curve, each point of the curve in the direction of the normal. So here you can see the normal. So for each point, it will be locally perpendicular to the curve. Then secondly, we will move it with certain velocity. And we will have a velocity map that is defined for each pixel. And we want the velocity to be large when we have flat region with no features. So then we should go fast. But if we have an edge, then we want to stop because we want the curve to stick to the edges. So basically we will calculate the image gradient, and the velocity will be high when the gradient is low, and will be low when gradient is high, because high gradient means edge. So actually it can be actually inverse gradient magnitude of the image intensities. Now finally we need to evolve this curve. So evolving the curve means changing it in time, and we will do that according to the differential equation. So derivative of this curve with respect to time will be defined as velocity times the normal. So velocity is defined on for each pixel, and the normal is defined for each point of the curve. Okay, so that tells us which direction should we go and how fast we should go. Now, the problem with this is that the optimization is quite difficult. The methods exist for active contours, of course, but it's not ideal setting. And there is actually a better way to do it through implicit curve representation using level sets. So representation of curves through level sets is defined in a way that we have a level set function, and this function is now defined on a grid of an image. So that creates much easier situation. We call it phi. And when this function is equal to 0, that will be our curve. Okay, so this is a zero isoline of the level set function. So here, this is a very simple example. It's just a Gaussian, and this is a zero plane. So if we cut through this Gaussian, we get this circle here. So on the circle, the level set function will be equal to zero. Inside, it will be positive. Outside, it will be negative. Now, how do we evolve this level set function to fit to the edges in the image? So the level set function will be updated based on the gradient magnitude of this level set function. So not the image, the level set function. We will again have the velocity for each pixel, and that's exactly the same as we had for the active contours. And we will have an equation how to evolve the level set function in time. So the derivative of the level set function in time will be equal to velocity times the gradient magnitude of the level set function. So this is actually very simple. The big advantage is that this is defined on the grid of the image, so it's easy to optimize. So as I said, the advantage is that it's easy to implement because level set function is on the image grid. And because it's defined through differential equation, we have the gradient and we can use gradient descent in a straightforward manner. This might not be the most optimal optimization method, but it's the most simple and it would work. Obviously, there are a more complex variation that might be more robust. Now, another advantage of the level sets is that they can adapt to any topology because they are defined implicitly. So for example, from a curve, you can create a hole or you can merge two curves together. So you see that here, this level set actually defines two different closed curves. And as it evolves, this can merge or another hole can appear. And of course, this was just a simplest possible design that because I wanted to demonstrate the main idea to you. And in our example, we had inverse gradient magnitude velocity to attach the curve to the edges in the image, but this doesn't have to be our objective. We might have a different application specific velocity function, so you can design it specifically for your application. We can also impose additional smoothness constraints to regularize the curves depending what we want to achieve. And also extension to surfaces is straightforward. It works exactly the same as for the curves. I want to just now go through a few applications. So this is a coupled level set for a segmentation of neonatal brain MRI. So in this application, we have 3 level sets. So here you can see schematic picture. The red one is for segmentation of white matter, gray matter surface. The blue one is gray matter CSF surface, and the green one is the outer boundary of the CSF and the background. Now, this is not simply based on the edges, but this technique incorporates intensity information. So something like the likelihood based on Gaussian mixture model. It also incorporates probabilistic atlas, and also it has a cortical thickness constraint to make it more robust. And here you can see result. This is the segmentation that you get based on intensity. And you can see that it's very pixelated, doesn't look very beautiful. And then if you feed level set to it, you get much nicer, smoother contours for the segmentation of this neonatal MRI. Final thing I want to talk about is how we combine level set and machine learning, because this is kind of cool now. Machine learning and deep learning are very popular, and a level set has disadvantages. For example, they need very good initialization. So we might as well try to see whether we can find a way to combine it with machine learning, and it turns out that it can be actually quite simple. So let's say this is our data that we've got. We've got some brain MRI images, and we have the contour of the white matter or white matter surface if it's in 3D. So if we want to train a machine learning model using this data, first thing we can do, we need to calculate the level set function. And this can be done through distance transform. So this distance transform assigns to each voxel the distance from nearest point on this curve. So this can be calculated quite easily using an algorithm that is similar to the region growing. And once we have the distance transforms for all the different images, we can train a machine learning regressor such as CNN on a random forest to predict the distance transform from the image. Just to go back a little bit to the distance transform, you can see that these red values are positive, so that's inside the white matter, and yellow, green, and blue are negative, so that's outside the white matter, and you see very far away it's very negative. So this is our training part. So we trained some machine learning model. We input the the image and get the distance transform. Now, if we have a new image and we would like the contours, we can use our trained machine learning model to predict the distance transform. And then we need to calculate the zero contour, which is here in white, and that's our curve. So actually very simple and cool. Now let's have a look at another application. So this time we don't really combine machine learning and level set, but we use level set for post-processing. So this application is segmentation of pancreas in CT. And you see that it's very difficult because the contrast is rather poor. So what the authors of this paper did, they segmented it in several steps that are sequential one after each other. First, they localized the pancreas using label propagation, and this is something that we will see next week. The reason for that is probably that CT images tend to be very large and don't fit on GPU, so it's good to find verities first before training a CNN. It might also be that intensities are really similar everywhere in the image, so that makes it difficult for CNN to localize, I assume. That's why they did it. Then we train on CNN to obtain a segmentation, but you see here that it doesn't work so great. The contour is not very nice. So what they decided to do about it is to use some post-processing. So first of all, they remove residual other tissues using intensity-based clustering. And in their case, it's fuzzy C-means clustering, and this is very similar to Gaussian mixture model. And finally, they fit a level set to image edges to refine the segmentation. So as I said, level set need to be initialized really well. So if they have a decent segmentation, they can use it for initialization, and they just evolve the level set a little bit to stick to the edges better. And that way they obtain much better segmentation than they originally had. So this is all that I wanted to tell you today. So let's summarize what we learned. So first of all, we learned that intensity-based image segmentation can be posed as a clustering problem and can be solved by, for example, k-means or Gaussian mixture model algorithm or fuzzy C-means that we didn't cover, but is similar to these two. Next, we covered probabilistic EM segmentation, and we saw that it allows us to model various image characteristics such as inhomogeneity or deal with the noise or include spatial prior information, like to tell us where the individual structures that we want to segment are located. Alternative segmentation methods that we covered include thresholding, region growing, graph cuts, and level set. And finally, we also looked at relationship of this classical segmentation model with machine learning and deep learning segmentation techniques. So you know that deep learning, machine and deep learning segmentation techniques are very powerful and very popular. So But the advantage of classical techniques is that they do not require training data, which that's why they might be preferable. But they also can inspire novel machine learning architectures, as you've seen with the level set, or help to refine the segmentation results. So this is all for today. We will have a second segmentation lecture where we will cover label propagation and also how we evaluate the segmentation results. Thank you for listening.